Good morning to everyone. Today's our topic is about quantum key distribution. So the topic is quantum key distribution. Introduction to quantum key distribution. Quantum key distribution is a method for secure communication based on quantum mechanics principles. It allows two parties to generate a shared secret key with theoretical unbreakable security. Quantum key addresses the vulnerabilities of classical cryptography by leveraging quantum properties. So the classical versus quantum cryptography. So the classical cryptography relies on computational difficulty which can be vulnerable to future algorithms and quantum computers. Quantum cryptography uses the laws of physics to ensure security, not just computational assumptions. So without computational assumptions also the quantum cryptography use the laws of physics to ensure the security. So the quantum key distribution provides a way to detect eavesdropping, ensuring the integrity of the key exchange. So the basic principles of quantum mechanics in quantum key distribution. Quantum superposition allows particles to exist in multiple states simultaneously until measured. So the no cloning theorem prevents perfect copying of unknown quantum states. These principles underpin the security features of quantum key distribution protocols. So in this image we will see the quantum key is transferred from Alice to Bob. So the Alice is the responder and the Bob is the responder. So the Bob will take the information. So Alice will send the information and U is the so the BB84 protocol developed by Bennett and Brassard in 1984. BB84 is the first practical quantum key protocol. It uses polarized photons to encode bits in two conjugate bases. Any eavesdrop attempt introduces deceptible errors, accelerating the communication parties. So the quantum states and encoding. Photons are commonly used as quantum bits. So the qubits in quantum key distribution systems. Polarization phase or time bin are typical methods for encoding quantum information. Accurate preparation and measurement of quantum states are crucial for secure key generation. So the quantum channel and transmission. So the quantum key distribution typically employs optical fibers or free space links to transmit quantum states. So here we transfer the quantum states, not the quantum bits. So the quantum channels are susceptible to loss and noise, which can affect the key rate and security. Maintaining low errors rates is essential for the effectiveness of the quantum key distribution systems. So the eavesdropping detection. So when there is a eavesdrop, so we will detect how we will detect them. So any measurement by an eavesdrop disturbs the quantum states, which can be detected. Alice and Bob compare a subset of their data to estimate error rates. So if error exceeds a threshold, the key is disgraced to prevent security breaches. So the key shifting and reconsideration. After transmission, Ali and Bob perform basis reconciliation to identify matching measurement bases. So then they use classical communication to transfer error correction. So this process results in a shared raw key, which is further proceed for privacy amplification. So the privacy amplification. It reduces any partial information an eavesdropper might have gained. It involves applying hash functions to shorten the raw key into a highly secure secret key. So this steps ensures the final key is secure even if some information leakage occurred. So the advantages of quantum key distribution. It provides theoretical unbreakable security based on physical laws. It can detect an eavesdropping attempts, enhancing trust in secure communication. Quantum key distribution is immune to future advances in computational power, including quantum computers. So the limitations and challenges of quantum key distribution. Distance limitations due to photon loss or noise in quantum channels. The need for specialized hardware and infrastructure increases implementation cost. So the integration with existing communication networks remains complex and ongoing. So the current technologies in quantum key distribution. So the current technologies in quantum key distribution. Advances include quantum repeaters to extend communication distances. Satellite-based quantum key distribution experiments demonstrate potential for global secure networks. So the developments in integrated photonics are enabling more compact and scalable systems. So the real applications of quantum key distribution. So the financial institutions use quantum key distribution for secure sensitive transaction. Governments employ quantum key distribution for classified communication channels. Researchers are exploring quantum key distribution for securing cloud data and future internet infrastructure. So the information will be in encrypted and plain text method. So the shared by a key. So the future directions and research. So efforts focus on increasing key rates and extending communication distances. Integration with classical networks to create hybrid quantum classical systems is underway. Development of quantum networks aims to connect multiple users via quantum links. So the global initiatives and standardization. Several countries have launched national quantum key distribution research and implementation programs. So international standards are being developed to ensure interoperability and security. Collaboration among academia, industry and governments is vital for advancing quantum key distribution technology. So the ethical and security considerations. Quantum key distribution raises questioning about the future of cryptography and privacy. So the widespread development could challenge existing security paradigms. Responsible developments and regulation are essential to maximize benefits and mitigate risks. Summary and conclusion. Quantum key distribution offers a revolutionary approach to secure communication. Its reliance on quantum mechanics ensures security that is fundamentally unbreakable. So, continued research and technological improvements will facilitate broader adoption of quantum key distribution.